So we've talked a lot about the Chinese restaurant process. Finally, we're going to get to the Dirichlet process now. Um, and so I'd like to kind of, before I get there, talk a little bit, expand on this idea of exchangeability, which I've mentioned a little bit about in the CRP already, right? So the idea here is that we have this generative process where customers come in one at a time, and we get a distribution over partitions. And interestingly, for the Chinese restaurant process, the order in which the customers come in and get sat around tables doesn't actually affect the resulting distribution over partitions. So in that sense, it's exchangeable, right? So we can take our customers and exchange the order in which they enter the restaurant, and it doesn't really matter. Okay. So this is an example of what's called exchangeable random partitions. Basically, it's a random partition, and it is exchangeable. Okay. So and I think that this is quite a useful property to have when you're modeling data, particularly because if you assume that your data set doesn't if your data set, if the way you order your observations in your data set doesn't really matter, then you're basically making an assumption of, should be making an assumption of exchangeability about your data. And so you should construct models which are exchangeable as well. Okay. So I'd like to give two examples of random partitions which are not exchangeable, just to, I guess, help with a bit of intuition. The first example is preferential attachment. So this is an idea that came out in network models, right? So, and you can also think about the Chinese restaurant process as a preferential attachment model, right? So the idea here is that elements are going to get inserted into the model one at a time, okay? And every time we have a new element, we could either insert it into an existing cluster or maybe into a new cluster, okay? So you start with one element, and then the second one could either enter here or there, third one is here, here or there, and so forth. And in some of the network modeling models that people in kind of random networks have explored, they have this idea of a preferential attachment model where you may have, for example, when you have a new element coming in, the probability of it joining a cluster that's large is large, so the probability is large. But then you may kind of reserve a certain probability delta for creating a new cluster. Okay, so in this case, the probability that number 8 joins one of these 4 clusters is going to be 1 minus delta times 3/7. So higher probability of joining a large cluster, smaller probability of joining a smaller cluster, and so forth. And probability of joining a new cluster is a fixed constant delta. Okay, so this is a different way of parameterizing a preferential attachment model, which is different from the Chinese restaurant process. Okay, it turns out that in this sort of models, they are not typically exchangeable. Okay, and it is useful in the network modeling case because you could think of elements that join the network early on may have a larger effect on what happens in the future because they were kind of like first movers in the market or something. Okay, so that's kind of nice, but it is not an exchangeable model. You're making an assumption that the elements are entering into the network or into the clustering over time, and the elements that enter first has a larger effect in some way than elements that enter later. Okay, so that's not an assumption of exchangeability. Okay, so a second example is a uniform partition. Okay, so let's imagine that we have our data sets over 4 data points. Okay, so these are all the different partitions that we could have over the 4 data points. And let's say that we would like to use prior over partitions that's uniform. We don't want to make any assumptions about our data. Okay, so there are 15 different partitions, so we can give 1/15 probability to each of those partitions. But then you could think about, what if actually instead of observing all 4 data points, I only were given 3 data points to begin with? Okay, should you then be working with uniform partitions over the 3 data points, or should you then be working with taking the uniform distribution over partitions of the 4 data points and then marginalizing out the 4th one because you didn't observe it? Okay, if you do that marginalization, what you could show easily see is that actually, if you have a uniform partition over 4 data points, then the marginal distribution over partitions of the 3 data points here, where we kind of ignore the 4th data points, is no longer uniform. Okay, so in a sense, it is exchangeable when you look at partitions over 4 data points, but it's no longer exchangeable when you start thinking about data sets that could be changing over time. You could be observing more and more data points over time. Okay. So in a sense, the fact that the CRP is exchangeable is quite special and is kind of useful if you want to make this assumption that your data is not dependent, or your data set is not dependent on the way you index your data set. Okay. So I'd like to relate this idea of exchangeable random partition to more typically in Bayesian statistics, people have talked about exchangeability, but for different sorts of things. Okay. Typically, when people talk about exchangeability, it's in terms of exchangeability of a sequence of variables. So let's imagine that we have a sequence of data items x1, x2, x3, and so forth, and we'd like to model this sequence of random variables using a joint distribution, okay, over this sequence, right? And we say that the sequence is infinitely exchangeable if basically the joint distribution doesn't depend on the ordering of the data, okay? So mathematically, what you say is that it's infinitely exchangeable if for every finite n, so if we see a finite collection of data points, then the way the n data points are permuted in your data set, are indexed in your data set, doesn't affect your joint distribution. Okay, so the joint probability of x1 to xn is the same when you permute the set of n variables. Okay, so what this simply says is that ordering of data points does not matter, and it's often a sensible modeling assumption. Okay. So I've mentioned this already, but an infinitely exchangeable model means that the way data points are ordered doesn't matter, and it's a modeling assumption that may or may not be relevant to you. Okay, if your data comes in a time series manner, then maybe you don't want to assume exchangeability. But if you're just given a set of data points and say that they are kind of more or less, doesn't actually matter how they are ordered in that set, then maybe you want to assume exchangeability. A second point is actually that the fact of infinite exchangeability actually also implies that the model is unaffected by the existence of additional unobserved data points. Okay, so let's imagine that we have a data set of size n, okay, and we are told a priori that we like to predict, we like to learn something about our data set, and then we are asked to predict what would happen in the next m test items. Okay, so if we were to do that in a Bayesian manner, what we'd like to do is to define a joint distribution over x1 to xn. This is our data set, and then xn plus 1 to n plus m, which is our test set. Okay. If our model is not exchangeable, or it's not infinitely exchangeable, then this joint distribution would depend on m, okay, which may or may not make sense, right? So if your predictions actually is dependent on you being told how many test data points you're asked to predict on, then that seems to maybe a strange assumption to make. Okay, right. So yeah, so there are, of course, it's a modeling assumption. There are scenarios in which it's suitable or not suitable. Okay. So why did, yes?
Can you give an example of a situation in which exchangeability is not suitable?
So for example, a conditional random field is an example of a model which doesn't satisfy this property. So a conditional random field is typically used in, for example, natural language processing to predict things like the part of speech of each word in your sentence. Okay. Now, if you have a sentence of length 10 versus a sentence of length 12, that actually affects your prediction under a conditional random field, which actually in this case actually makes sense because the length of the sentence actually should have some effect on the predictions of the part of speech of the words in your sentence. Okay. So that's an example for which we are not assuming exchangeability. Okay. So why is exchangeability so important in Bayesian statistics? It's because of this result by Finetti, which is from a long time ago, and which the result is basically says that if we have a sequence of random variables that's exchangeable or infinitely exchangeable, then there will be a random probability measure G such that the marginal distribution of x1 to xn can be decomposed in the following way. Okay, so it's an integral over G. So G is a random variable, is a random probability measure, and P is simply the distribution over G. Okay, and it's an integral over G of a product I from 1 to n of G of AI. Okay, I'd like to parse this a bit. Okay, so this here is the joint probability that the random variable x1 belongs to the set A1, x2 belongs to the set A2, and xn belongs to the set AN. Okay. Over here, what we are saying is that conditioned on G, then the probability of xi belonging to the set AI is simply going to be given by G of AI. So G is basically our distribution of each of the xi's, which are going to be IID conditioned on G. Okay, and each of them has a distribution given by G, and G itself is random and has a distribution given by P. Okay. Right. So given G, the random variables are IID distributed according to G. Okay. In a sense, this random probability measure kind of captures all the dependent structure that underlies this set of random variables. Okay. So when I say random probability measure, it's probably a little bit confusing, I guess, for you guys. So I'd like to kind of parse that a bit as to kind of what that actually means. Okay. So before we talk about random probability measures, what does a probability measure mean? So this is a little bit of just a bit of probability theory, a kind of measure theoretic probability theory. Okay. So a probability measure is simply a mathematical object that describes a distribution. Okay. What is a distribution? A distribution is basically basically a function, okay, which P from a space of events to a space of probabilities, and basically A is an event, so A is simply an event that could or could not occur. Okay, and P of A is simply the probability that the event occurred. Okay, it's a function that satisfies certain properties that would make it a probability measure. Okay, so for example, the probability of the zero event, of the empty event, will be 0. Okay, so which kind of makes sense, right? The probability of two events which are disjoint, they're disjoint. If A and B are disjoint, then the probability of A union B, so the probability of A happening or B happening, would be the sum of the probability of A and the probability of B. It has to satisfy this property for it to be a probability. And the probability of the complement of A is simply 1 minus the probability of A. Okay, it has to satisfy all these properties to make it a probability measure. And basically, a random probability measure is a random function that satisfies the properties of a probability measure. Okay, so you've seen random functions already in Gaussian processes, I guess. And in those cases, in the case of Gaussian process, it's simply a random function from an input space to an output space. In this case, we have a random function, but they have to satisfy the properties of a probability measure. Okay. Another way of thinking about a random function is that it's simply a collection of an infinite collection of random variables. Okay, so it's a collection where indexed by A, where A is an event. Okay, so and such infinite collections of random variables are stochastic processes. Okay. So just to give you an example of exchangeability and Finetti's theorem, okay, and random probability measures. Okay, so this example is very simple. It's called a Pauli urn. Okay, let's imagine that we have, I guess this is not really an urn, but think of this as a urn, like a bottle that contains a number of balls. I have a number of white balls and a number of black balls. The number of white balls is A and the number of black balls is B. Okay, and what I'm going to do is the following. So I'm going to construct an iterative process that goes as follows. I'm going to, at some iteration, say in the first iteration, there are A equals to 2 white balls in here and B equals to 1 black ball. I'm going to draw one of the balls uniformly at random from this urn. Okay? And of course, the probability of drawing a white ball is going to be 2 divided by 3. And the probability of drawing a black ball is going to be 1 divided by 3. Okay? So with probability 2/3, I'm going to get white, and probability 1/3, I'm going to get black. Okay? And if I get a white, then what I'm going to do is I'm going to put in one new white ball into the urn. Okay, so something, oh, in this case, actually, I drew a black, so I'm going to put in a black ball. Okay? At the second iteration, now we have 2 white balls and 2 black balls, so the probability of drawing white is going to be 2 over 4, and drawing black is going to be 2 over 4 as well. Okay, so I'm going to draw one of that and say I might get a black ball again. So now the probability of the next iteration I'm going to get a white is going to be 2/5 and 3/5 for black. Okay, and I can keep on repeating this. Every time I draw a ball of a particular color, I'm going to put in an additional ball of the same color back into the urn. Okay? So this introduces dependencies in the sequence of draws. Okay? So we might get something like this, and so forth. Okay? Okay, so that's it. So we can, oh yeah, oh, sorry. Lots of balls, sorry. So suppose that after n iterations, we actually drew nw white balls and nb black balls. Okay? And you could ask, what's the probability of this sequence of draws of whites and blacks and of sequence of colors, basically? You can write down, multiply all the conditional probabilities together, and that gives you the probability of this sequence of draws, okay? Which we can rewrite in this way, where this thing here is a rising factorial in A, so A plus 1, A plus 2 with nw terms, so it ends up with A plus nw minus 1. And similarly, this is a rising factorial starting from B, and this is a rising factorial starting from A plus B. Okay? So that's the probability of this sequence, and you see that actually this probability of this sequence doesn't actually depend on the ordering of white balls and black balls that you see. All it depends on is the resulting number of white balls and black balls. Okay? So which means that this Polya urn scheme defines this sequence of random variables, the colors of the balls that you saw, that you drew at each time. And this sequence is exchangeable. It doesn't depend on the ordering. Okay. So we can apply Definity's theorem and say that there is a random probability measure G such that the joint probability of the first ball being of color C1, the second ball being of color C2, and the nth ball being of color Cn, it can be written as this integral here, which is basically, we can think of this as the marginal distribution of a model in which we have a latent probability measure G, and then given G, we have our x's, which are our sequence of n colors. Yes. Does it work? Oh, blackboard. Okay, that works too. Yes. It's just going to be G, and then xi, and we have a plate over xi. Okay? So this model is saying that we first draw G, okay? We first sample G, and then conditioned on G, our x's are going to be conditionally IID with distribution given by G. And that's what the functional form here is saying. And basically, this term here is the marginal probability of the x's taking on particular values where we integrate out G. Okay. Okay. So in this case, we only have two colors, white and black. Okay. So a probability measure over this space white and black can be equivalently cast as a single number between 0 and 1. So this number could be to just tell you the probability of white, and then 1 minus that number is the probability of black. Okay, so a random probability measure is just a random number between 0 and 1. Okay, that's what this random probability measure is. And the question is, what is the distribution P of G under the Polier-N scheme? It turns out that it is simply a beta distribution with parameters A and B. Okay, so a random probability measure in this case is simply a random variable on the uniform, on the standard, on the unit interval 0, 1. Okay. Right, so this is a very simple situation where we see that we have a sequence of random variables, the colors of the balls that we drew, and this sequence is exchangeable, and then once we apply Definity's theorem, we get a beta distribution out. Okay. So coming back to the CRP, we know that it is an exchangeable random partition. I haven't really described to you how is a random partition related to a sequence of random variables. Okay. So we can construct a sequence of random variables from an exchangeable random partition in the following way. For every cluster in our partition, I'm going to define theta star C to be drawn IID from some distribution H. Okay? And then for every item I in our set 1 to n, I'm simply going to say that theta I is going to take on the value theta star C, where C is the cluster that I belongs to. Okay. Yes, and coming back to the CRP mixture model that we saw previously, the theta i's are actually the parameters of the cluster that data point xi belongs to. Okay, and xi is going to be some. We have an observation model given by f, basically. Okay, so here what we get is that the sequence of thetas we can show that it's going to be exchangeable. It's going to be an exchangeable sequence of random variables because the CRP is exchangeable. Okay, so now we can apply Definity's theorem and say we have this sequence of random variables that's exchangeable. So Definity's theorem implies that there's some random probability measure G which makes them IID. We have a model which looks like this, where instead of x we have theta. Okay, yeah, instead of x we have theta here. Okay, so the question that we'd like to answer is, what is this G? Okay, that's going to be the Dirichlet process. And what properties does this Dirichlet process have? Okay. So before I move on to that, I'd like to just say a few words about exchangeability. So it's quite, this idea of exchangeability and Definity's theorem is very important. It plays a fundamental role in a sense, the philosophy of Bayesian statistics. The reason is because we are making a pretty innocuous assumption, right, that our data set is exchangeable. We don't care how it's ordered, okay? And just from that very innocuous assumption, what we get from Definity's theorem is that the way we should be modeling our data set is using a hierarchical Bayesian model where we have some latent variable G that captures all the structure in our data, and conditioned on G, the data set is going to be IID. Okay. And further, this is a Bayesian approach in that G here, this latent variable that we don't know about, is actually a random variable. And to do Bayesian inference, all we need to do is to specify a prior over G, and then compute the posterior distribution of G given our data set. So what I've described here, this is exchangeability of a sequence of random variables, and there are generalizations that lead to basically Bayesian models for richly structured data. Okay? So for example, if you have a network data, you might assume that the nodes in your network could be exchangeable. Okay? So imagine social network, and somebody gave you a collection of people and who are friends with whom. And if they give you this if they gave you this collection of people and say that actually the order in which I gave you this collection of people doesn't actually matter, then we are making an assumption that somehow this set of n people are exchangeable in some way. Okay? And just by that assumption, you can actually, there's a generalization of Definiti's theorem which leads you to a Bayesian model for how you should be modeling your data. Okay, I'll come back to this tomorrow. Right, you can talk about hierarchical exchangeability and as kind of different generalizations of exchangeability as well. Okay, right. So I'll kind of the next section is about properties of the Dirichlet process. Okay, the first property that we'll observe is that what we get is the following. So we know that I've already told you that your random probability measure G is going to have a distribution given by a Dirichlet process, and it's going to be parameterized by the two things that, so by alpha, which parameterizes our CRP, and by H, which is the distribution that we are drawing the parameters of each cluster from. Right? And then condition on G, the theta i's are going to be IID draws from G. Okay. Now the fact that each of the theta i's, every draw from G, there's going to be a positive probability that that other draws take on exactly the same value, right? Because every theta I in our Chinese restaurant, every I is going to belong to some table, and there's always going to be a positive probability that future customers sit at the same table and take on exactly the same value of theta I. Okay? What that means is that every draw from G will have a positive probability of being repeatedly drawn in the future. Okay? What that implies actually is that G is simply an atomic distribution. Okay? We can write G in the following way, okay? Where the atoms are given by theta star k, and the mass associated with theta star k is simply going to be given by pi k. Okay? So if you're not familiar with this notation here, what this is a very simple distribution. It simply says the following. With probability pi k, we're going to take on value theta star k, and that's it. And there's possibly an infinite collection of these values. Of course, the pi k's have to sum to 1, and they have to be all not positive. Okay. Right. So we could ask. So we know that our Dirichlet process has to take on this functional form where we have an infinite collection of atoms with particular weights. Okay. The question then is to understand the distribution of G. It's sufficient to understand the joint distribution of the weights of the masses on the atoms and the locations of the atoms. Okay? And there's kind of two ways of describing this. One's called a stick-breaking construction, and another one is called the Poisson-Dirichlet distribution. Okay. So we can get the stick-breaking construction actually by kind of going back to the CRP and looking at how that leads to the stick-breaking construction facts. Okay. So recall that the first customer is always going to sit at the first table. Okay, so let me write down kind of like the decision for future customers in the following way. I'm going to have a table 1 here and other tables there. And if you think about the second customer, what's going to happen to the second customer? The second customer is going to sit at table 1 with probability proportional to 1, and sit at another table, some other table, with probability proportional to alpha. So customers 2 and 3, let's say that they sit down at table 1, and let's say that customer 4 sits at the new table. So what that says is that 1 and 2 comes down here, customer 4 comes down here. Okay, and when the customer 4 sits at the new table, we can say that that's just going to be table 2. Okay, so now we have created a new decision point in which we could either, if we come down this branch of the tree, we could say, is it going to sit at table 2 or maybe yet another new table? Okay, and if you think about the distribution for customer 5 at this point is going to sit at table 1 with probability proportional to 3, and at some other table with probability proportional to alpha plus 1. And then if it sits at another table, then the probability of sitting at 2 is proportional to 1, and at the new table is probability proportional to alpha. Okay? And we can kind of repeat this. So 5 and 6, let's say, sits here, and 7 sits there. Now the counts get updated. So we have 4 here, alpha plus 3 here, 2, and alpha plus 1. Okay? And we just repeat this, right? So if you think about, and of course, customer 7 sits at a new table here, so we can create a new table for customer 7 and create a new decision point in here, in this diagram. And for customer 8, basically we start off at the top and we say with probability proportional to 4, it's going to sit at table 1. With 1 minus that probability, we're going to sit at another table. With probability proportional to 2, we're going to sit at table 2. With 1 minus that probability, we're going to sit at another table. With probability proportional to 1, we're going to sit at table 3, or maybe create a new table with probability proportional to alpha. Okay? So that's kind of the sequence of decisions that's kind of created, in a sense, by the Chinese restaurant process. Okay? And if you look at this, what you notice is that actually at each point here, the decision of going left or right down this diagram is exactly the Polya-Earn scheme, right? So with a Polya-Earn scheme where we initially start off with A of equal to 1 and B equals to alpha, okay? Right. So the initial values are A equals to 1, B equals to alpha, okay? So if you think about the sequence of decisions that is made at the top here, we're gonna basically get we can kind of go back to Finetti's theorem and say that the decisions are equivalent to first drawing a random variable from a beta 1 alpha distribution, and then using that as the probability of sitting at table 1. And similarly, at this point here, we draw from a beta 1 alpha, and that gives us the probability of sitting at table 2 if we didn't sit at table 1. Okay. Right, and that's exactly what the stick breaking construction is. Okay, so so that gives you this sequence of independent betas, which gives you the stick breaking construction. So here's a different way in which we could think about what I've just described. My sequence of betas is going to be given by Vk, and they're going to be IID draws from beta 1 alpha. And pi k is going to be the probability of sitting at table k. Okay? And it's going to be given by basically the product of the probability of not sitting at all the previous tables times the probability of sitting at that table as we go down the tree that we saw just now. Okay? So those give you the masses, and then at each table we're going to have a parameter drawn from H, and that's going to be the locations of the atoms. Okay. Yep. So the pi k's are decreasing on average, but not strictly, of course, because it's we can think of this is called stick breaking because we are taking a stick of length 1 that represents the fact that the probability measure has to have a total mass of 1. Total probability of 1 over all possibilities. And the probability of sitting at the first table is going to be proportional to, is going to be actually exactly equal to pi 1. And then the probability of sitting at the second table is going to be exactly equal to pi 2. And of third table is pi 3 and so forth. Yes?
Can you please read again out how do you say the sum of k equals to 1 to k the half?
Mm-hmm.
So in like an informal way.
Uh-huh.
This pi k times delta.
Yeah. So what this thing is simply, this is a distribution where with probability pi k, if we draw from that distribution, with probability pi k, we're going to take on value theta star k. Okay. Yep. Okay. Okay. So I guess I'll skip all this. So that's one construction for the Dirichlet process now. It's a very explicit construction, okay, that gives you explicitly what this functional form looks like and what's the joint distribution over the unknowns here, the pi's and the thetas. Okay. You can also use a similar sort of argument to argue to actually derive the following. Let's imagine that we have some event A Okay, some event. So our probability measure is going to live over a space, right, given by theta. And let's look at a measurable subset A, and we can ask what's the probability that the random probability measure, no, what's the distribution of the mass that the random probability measure gives to this subset, okay? And that's going to be a random variable because the probability G is random, okay? So basically, what's the marginal distribution of G of A? You can use the same sort of argument, actually going back to the Polya-Ern scheme, to actually derive that that marginal distribution of this random variable here is simply going to be beta with parameters now alpha times h of A, where h is our distribution over the parameters of each cluster. Okay, and this is basically alpha times 1 minus h of A. Okay. Right. So I'd like to kind of give names to these two parameters of the Dirichlet process. Alpha here is often called the strength parameter, or the mass, or the concentration parameter. Okay. And h is often called the base distribution here. Okay. The fact that G of A is beta distributed, you can immediately write down what is the mean and the variance of this random variable. Okay, and you can easily see that actually the mean is simply h of A. Okay, which means that actually the mean of G is simply going to be h. Okay, so we can think of h here, the parameter of the Dirichlet process, as basically the mean of the Dirichlet process. Okay. And if you look at the variance, we're going to get some quantity up here divided by 1 plus alpha. And basically, the larger alpha is, the smaller the variance is going to be. Okay? So basically, the larger alpha is, the more concentrated the Dirichlet process is going to be around its mean. Okay? Which is why it's called a concentration parameter. Okay? You can generalize this to the following. So suppose that we take our space, our probability space, big theta, and we partition it into a finite collection of subsets, say A1 to AK. Then we could ask, we can look at the marginal distribution of this vector here, G of A1, that's the mass that our probability measure G assigns to this subset. G of A2 is the mass that our probability measure G assigns to this subset, and G of A3, G of A4, 5, and 6, and so forth. Okay. So this is going to be a probability vector because the total probability assigned over the whole space has to be 1 because G is a probability measure. And G is random, which means that this vector here is going to be a random vector, a random probability vector. And in fact, we could ask, what is the marginal distribution of this vector here? And it's simply going to be given by a Dirichlet, okay, with those parameters. Okay. And in fact, this can actually be used as the definition of a Dirichlet process. And this is actually the way Ferguson, back in 1973, actually first defined a Dirichlet process. He said that I would like to have a distribution over probability measures such that given a partition of my space, the marginal distribution over this vector is going to be Dirichlet distributed. Okay? And he chose the Dirichlet because it's computationally tractable. Okay? Yeah, and that's it. Okay, so so if you look at this, it's kind of not really clear how is it that we actually get the atomic nature of the Dirichlet process from this definition, okay, here. But actually, you can look at what, if you actually try to draw from this, you can actually see what happens. Okay, you can see, yep. So here, my probability space is going to be the unit interval on 0, 1. Okay, and up here, what I'm going to, the height of this little rectangle here is going to be simply the probability of this part of the space. And since this is the whole space, that probability has to be 1. Okay, And what I'm going to do is I'm going to kind of split this space up into two halves, from 0 to 0.5, and then from 0.5 to 1. And then we could ask, what's the probability? What's the probability that, no, sorry. Yeah, what's the probability that G will assign us some mass to this part of the space versus that part of the space? Okay. Oh, sorry, what happened? Actually split into actually four different four different intervals here. So G of this first quarter of the unit interval is going to be, actually this is 1.5. Actually, you have to multiply that by 1/4 to give you the probability of this part of the space. Okay, so that the area of under this rectangle actually gives you the probability of this part of the space, and the area of this rectangle here is going to give you the probability of this part of the space, and similarly here and there. Okay, and you can kind of like keep on refining our partition of this space into finer and finer intervals, and we could ask what's the probability of each interval, okay, under the Dirichlet process. And what you find is actually as the intervals get finer and finer, you get actually a draw from the Dirichlet process, which looks like it's kind of atomic, basically. Each of these vertical lines is basically telling you that there's some atom with a mass that's proportional to the height of this line at that point of the space. Okay. And that's kind of how you kind of see that that the definition of the Dirichlet process given by Ferguson actually leads to an atomic distribution. Okay. Yep. You can also look at what the posterior looks like. Okay. So the reason why Ferguson chose a Dirichlet for his marginal distribution over the partitions is that it's kind of computationally tractable. Okay. And actually, what that kind of means in particular is the following. So we have a random probability measure that's a Dirichlet process distributed, and we can define a sequence of random variables that are going to be IID draws from G. Okay, so that's what Definity's theorem gives us from the CRP. And then we could ask, given observations of θ1 to θn, what is the posterior distribution for G? And because of this conjugacy between the Dirichlet and the multinomial, you actually get that this kind of carries over to the Dirichlet process, so that conditioned on θ1 to θn, we actually get that the posterior distribution for G is also a Dirichlet process with an updated concentration parameter and mean, basically. Okay. Okay. So, and the fact that our kind of probability measure is atomic actually leads to this clustering property, which leads to the CRP, basically, right? Because we know that because G is atomic, the n variables θ1 to θn can take on they can take on repeated values, which means that if you look at the distinct values, they're going to be, let's say there are k distinct values, k could be less than n, okay? And if we define the distinct values to be θ1 star to θk star, then this actually defines a partition over such that I is in cluster k if and only if θi takes on value θ star k, okay? And this actually induces a distribution over partitions, which you could show is exactly the Chinese restaurant process. Okay. Actually, I'm going to skip all this. Are there any questions so far? No. Yes?
I just had sort of one question. Not exactly related, but we had some people come in and talk about causality, and that seems to be a complete violation of this, exchangeability.
Why is it inconsistent with exchangeability?
Because, like, let's say one person would cause more people to what if there's like strange attractors in the group, like who would cause other people
Okay. So, so in that case, you're kind of assuming that there's some sort of order in which people are acting in the world, and that order breaks exchangeability. So you're just, so I guess that's not really a contradiction. What it is saying is that you are trying to model your data using a kind of a model which is dynamic in nature, is changing over time. Right? So it's not exchangeable.
So some of the causal people just saying that they could prove that there was a time ordering to the data, so that you're just saying that that just breaks exchangeability.
Right,
So
yeah.
that's really causal.
Yeah, it's not anything to do with causality, I think, yeah. Yeah. Okay. Any other questions? Nope. Finally going to move on to part 2, which is kind of moving beyond the Dirichlet process. Okay. And in particular, there'll be 3 things that I'd like to talk about in the last 40 minutes, I guess, which is hierarchical Bayesian Nonparametrics, Pittman-Yaw processes, and Indian buffet processes. I'll see how far I can get to. Okay, I'll start with that. So one of the interesting ideas that's come out with from Bayesian Nonparametrics, I think, is that we can make use of this random kind of this stochastic processes like the Dirichlet process, the Gaussian process, as kind of building blocks in building more complex models. Okay. And the nice thing with kind of taking the Bayesian probabilistic modeling approach is that it's quite easy to construct these complex models from simpler building blocks. Okay. And one way in which you could construct more complex models from simpler models is using hierarchical Bayesian modeling. And here, what I'm going to do is to construct more complex models from simpler building blocks, which are themselves Dirichlet processes. Okay. And the motivating example is coming from topic modeling. Okay. So here, the idea is that what we'd like to do is we're given a collection of documents, and we'd like to organize the documents in terms of a certain number of topics, okay, where each topic is, you can think of as some semantically coherent set of words that tend to co-occur together. Okay. So here's a little example that came from, I forgot which of these papers is it, but basically they have analyzed, I think, some collection of scientific papers and looked at the words that tend to co-occur together. And we see that the words that tend to co-occur together tend to kind of make semantically related, they tend to be semantically related. So for example, this collection of words that tend to co-occur together seem to be kind of about a topic which has to do with computer science, right? While this topic here has to do with genetics and evolution, and maybe this one might be having to do with, you know, diseases and so forth. Okay. And a very popular model for this modeling topics is latent Dirichlet allocation. Okay, so here what we're going to do is we're going to model a topic as a distribution over words that tend to co-occur together, and each document in our collection of documents as a mixture over topics. Okay, so the generative model is very simple. Actually, here's the graphical model here. So the outer plate is going to be my plate over documents, and the inner plate is going to be my plate over the words that occur in that document. And the way we're going to model this collection of words, collections of words, is that for the ith word in a document J, I'm going to model in the following way. I'm first going to pick a topic that it could belong to from some distribution pi j, which is basically describes the collection of topics that occurs in that document. Okay, so we're going to first pick a topic from that pi j, and then given a topic, we can now generate a word from a topic-specific distribution over words. Okay, so that's that part of the generative model. We like to place priors over the distribution over topics here and the distribution over words in each topic here. We can use a Dirichlet prior here and another Dirichlet prior here. Okay, so that's kind of a typical Bayesian approach. And you can think of this as this model here actually as a multiple mixture model. So every document is going to be a mixture model, and we have multiple documents that gives us multiple mixture models. but they have some sharing of information across the mixtures, right? So all the topics are going to be shared across the different documents. All the topics are going to be shared across the different documents. So one question we might ask is, how many topics can we find in our collection of documents? Okay, how many topics do we need to describe the words that occur in our a collection of documents? Okay. So in a sense, if we, instead of trying to think about a finite mixture and then trying to infer k, the number of topics, we can try to take a non-parametric approach as well. Okay, since we've learned about the Dirichlet process and how we can use it for clustering. So here we're trying to somehow cluster words. Okay. So we can use a Dirichlet process for each document. So let's say that we have two documents, document 1 and document 2. We may have a Dirichlet process G1 for document 1 and another Dirichlet process G2 for document 2. If the base distribution of our Dirichlet process is smooth, if it's a smooth distribution, which it is in this case, we're going to take a base distribution which is actually itself a Dirichlet distribution. Okay, so it's going to be a smooth distribution. So the collection of topics are going to be the atoms in this Dirichlet process, and here we're going to have another collection of topics. Okay. Now, because the base distribution is smooth, the collection of topics in here will be disjoints from the collection of topics over there, right? Because all the atoms in here are going to be drawn IID from H, and if H is smooth, then if you draw IID from H here and you draw IID from H here, this collection and this collection will be totally disjoint, okay? Which is not what you want, right? Because what this is saying is that the collection of topics that you used to describe document 1 is totally separate from the collection of topics that you used to describe document 2 or document 3 and so forth. So that's not very nice because we would like to have sharing of topics across our documents, okay? So the solution is, the problem lies in the fact that our base distribution is smooth. So the solution is to just simply make it not smooth, okay? So in particular, we would like to make H be a discrete distribution, an atomic distribution. Okay. And of course, we'd like to place a prior over atomic distributions. So what prior do we have over atomic distributions? It's a Dirichlet process, right? So we can place a Dirichlet process prior on our base distribution that is shared across the two different Dirichlet processes down here. Okay, so this leads to what's called a hierarchical Dirichlet process, where we have a common base distribution G0, which is drawn from a Dirichlet process. Okay, it's up here. And then conditioned on G0, G1 and G2 are the two Dirichlet processes that describe the mixture over topics for the documents 1 and 2. That comes, both of them are going to be independent, independently drawn Dirichlet processes, but with the same base distribution given by G0. Okay. And we can kind of extend this to larger hierarchies as well. Okay. So graphically what's happening is that it's a hierarchy, right? So we can start at the top and we say, let's draw a Dirichlet process for G0. It might look like this. And then let's draw another two independent Dirichlet processes, G1 and G2. We might get two different random probability measures given by the blue lines there. Now, the location of each atom here has to be drawn from one of these atoms. So which means that the collection of atoms in here is exactly the same as over here. And similarly, the collection of atoms in here is exactly the same as over there. The only difference between this and that is that the masses on each atom are different in these two Dirichlet processes. Okay? Which kind of makes sense because in the topic modeling case, what we like to do is to say that we have the same collection of topics across the different documents, but different documents could have a different proportion of each topic. Okay. Yep. So I guess this is the first slide with some experimental results, I think. So in this slide, what I'm doing is that we'd like to compare this of HDP, hierarchical Dirichlet process mixture model, this Bayesian Nonparametric approach to topic modeling, against LDA, which is a parametric modeling approach, where we also want to kind of infer the number of topics as well. Okay, so we do a model selection for LDA. So we try LDA on 10 topics, 20 topics, up until 120 topics. Okay, and we see that the task performance kind of like improves as we increase the number of topics, and then starts getting worse again. Okay, and that's fine. So which means that we believe that there are, if we believe that there are a finite number of topics, then there should be between 50 and 18 topics in our document collection. Okay. If we do the same thing for the HDP, then we get a test performance which is basically as good as the LDA. But to get this single number, we don't need to do model selection. We just run our model, we just run our inference on a single model, and that's it. Okay, so that gives us this number here. You can also look at the inferred number of topics under the HDP, and it's between 60 and 70 in this case, which is basically exactly right in the middle here. So they are kind of, in a sense, consistent with each other, the inference that you get. Yes? Perplexity is a measure, just think of it as a measure in which the better your model is, the lower it is. It basically, perplexity is how perplexed the model is, and the less perplexed, the better it is. Okay. Yes?
So is it possible to combine exchangeable priors with non-exchangeable priors? Because for topic modeling, I might think documents are exchangeable, but not words inside a document.
Yes. Actually, in topic modeling, there's this huge literature out there, and I think most of the non-exchangeable models that people have played with is actually not in terms of exchangeable documents but non-exchangeable words, but rather exchangeable words but non-exchangeable documents. So the idea is that we are trying to analyze a collection of documents over time. So for example, the collection of all papers that appeared in Science, in the journal Science, right? Then the papers that appeared in 1910 will be quite different from the papers that appeared in 2010. So we like to model this change in the topics that are popular in Science over the 100 years, for example. Okay, so that's a non-exchangeable document, but exchangeable words within each document. Okay, I'm going to skip this, but basically there's a combinatorial structure that is underlying the hierarchical Dirichlet process called the CRP. Okay. So this idea of kind of hierarchical Bayesian modeling, which I'm kind of describing here, is quite an important kind of overarching theme actually in modern statistics. It kind of brings in ideas from both Bayesian and frequentist statistics. Okay. And in machine learning, it's been kind of used for lots of problems like multitask learning and transfer learning and learning to learn and domain adaptation as well. Right. So the idea is that if you have 3 different data sets, then what you like to do is that if you believe that these 3 different data sets are somehow related, then you like to model them jointly. Okay. But you know that they are also different, so you like to model them using different parameters too. So one way in which you could model them jointly but with different parameters is to say that every data set gets its own parameter, but then you're going to introduce a prior over the parameters that is itself random, and it's this randomness that kind of like introduces dependencies and sharing of information across your modeling of the 3 different data sets. Okay. So you can imagine that this can be very useful in multitask learning, right? So you have 3 different tasks that are related. We model the 3 tasks with its own individual parameters, but you like to share information across your tasks. Okay. Yeah. So in hierarchical Bayesian nonparametrics, so for which the HDP is a particular example, the idea here is that we like to build kind of more complex models from simpler building blocks, but the simpler building blocks themselves could be stochastic processes too, like Gaussian processes, Chinese restaurant processes, and so forth. And that allows us to kind of build interesting models from more simpler blocks. Okay. And there's been lots of applications. I guess we're kind of like, there's a earlier review that I did with Mike Jordan that maybe you could refer to. Yep. Okay, so I'm just gonna start skipping bits that is not in the main flow of things. Okay. Okay, so another example in which you could use hierarchical Dirichlet processes is in hidden Markov models. Okay, so just to recap what a hidden Markov model is, we're going to assume that our data is now not going to be exchangeable. It's going to come from some time series domain where we observe our data one at a time, and we're going to model this using a sequence, a Markov sequence of latent states in our model. Okay. So one of the problems that people often encounter is, we have a hidden Markov model with a k states. Can we infer the number of states? Okay. Or maybe we'd like to not have to infer the number of states. Maybe we'd like to take some sort of non-parametric approach and take the number of states to go to infinity in some way. Okay. So it turns out that you cannot actually simply take k to go to infinity for exactly the same failure mode as latent Dirichlet allocation. What will happen is that if you take the usual approach and take k to infinity, you're gonna be led to a model in which at every time step of your model, you're always going to transition from the current state to a new state that you've never seen before, and you're always going to get new states and new states. And of course, every time you see a new state, there's no generalization across states because you never see the same state twice, okay, which is not very useful. But you can actually have some sort of a Bayesian nonparametric approach to infinite HMM by basically using a hierarchical Dirichlet process to define your infinite HMM. So that's a very nice application of this infinite HMM that I'd like to kind of highlight, I guess, that I think was the people that started working on this is Sharon Goldwater and Tom Griffiths and Mark Johnston. So here the problem is the following. In certain Asian languages, in English, for example, the words, you always have spaces in between them, right? But in certain Asian languages, actually, there's no spaces between the words. So it's very difficult to kind of segment the characters into sequences of words, basically. Okay? And in English, of course, in written English, you know exactly the boundaries between words. But often, actually, in spoken English, you don't actually know the boundaries between words. Okay? So for example, this one here is a sequence of utterance that says, you want to see the book. Okay? I guess this is coming from a data set where people actually recorded interactions between mother and babies, where they try to the data set is collected because people are interested in learning how do people learn how to speak, how do people pick up language from their environments. So one of the problems that you need to solve to pick up language is to say that babies don't learn by reading, right? They learn by listening. And when they listen, people don't actually pause between words. How can the baby figure out transitions between words from this sequence of utterances that the mother said? Okay. One way in which you could kind of model this is using an infinite HMM. So the idea is that we have our sequence of utterances here, and we're going to model this as a sequence of words, okay, with transitions between the words, and each word is going to generate a sequence of utterance. Okay, and basically you can think of this as in a sense, a clustering problem, where we try to cluster and segment this data into small sequence of words that tend to co-occur together. Okay, and of course, initially, we are never really told the number of words in the vocabulary, right? In fact, you can argue that actually, as you grow, you should, I guess, at this point, the vocabulary in my head is probably decreasing now. But as a baby, you're always learning new words all the time, okay? So, taking a Bayesian nonparametric approach is very sensible. You're kind of allowing the model to learn newer words as it sees larger and larger data sets. Okay? So the number of words is unknown, and of course has to be part of the output of the learning process. Okay? And we can use this infinite HMM to couple with kind of a model to generate strings of utterances to actually kind of model this learning problem. Okay? And this is kind of very nice work by Sharon Goldwater et al. Initially, and then a kind of Daiichi Mochihashi later on extended this to quite a complicated model that seems to work very well for segmenting Asian languages. Okay, so these are just some results. I guess I should tell you what P, R, and F is. I think this is precision recall and F score, which is some harmonic average between the two. Okay, basically, again, it's some measure of how well the model is doing. Higher is better. Okay, I think there are two models out there. Actually, I'm not sure. I think this is probably a standard model that was existing at the time. And there's a Dirichlet process version and there's a HDP version, which works pretty well. And then here we have a nested Pitman-Yaw process version that works quite well compared to the state-of-the-art at the time too for segmenting Asian, Chinese and Japanese languages. Okay, any questions about this? Yes? Efficiency. Computational efficiency or statistical efficiency? It seems that statistically it's quite efficient. Computationally, basically for these models, people do kind of MCMC sampling, and then they have to run it for quite a while. But okay, yes.
So can you put another layer of Dirichlet process so that you can do segmentation across different languages?
I guess people haven't tried that. The question is, if you're going to work with different languages, how should you generalize across languages? Because a word that occurs in one language probably is going to appear totally different in a different language, I guess. But there are quite elaborate generalizations to this. Yeah. Okay. I think I'll mention one a bit later. But the next topic I'd like to talk about is Pitman-Yaw processes, which is a generalization of the Dirichlet process that has some very nice power law properties. Okay. So since going back to the Chinese restaurant process, we see that it's described by this process in which customers come in at a time and they're sitting around tables with those probabilities. And we get this exchangeable distribution over partitions. Okay. There's a very nice generalization of this called I guess I'm calling it the two-parameter Chinese restaurant process because there's an additional parameter, D, in addition to the original parameter alpha. Okay. And this D parameter is between 0 and 1, and alpha here is greater than minus D. Okay. And basically, it's a Chinese restaurant process, but the probability of a customer sitting at a table is adjusted in the following way. The probability is going to be proportional to the number of customers currently sitting there minus the D parameter. The D stands for discount in this case. Okay, so we are discounting a certain. We are discounting the probability of sitting at that table. So if you have 4 tables here, then we're going to subtract D from here, D from here, D from here, D from here, and then so that the 10th customer will have probability of sitting at a new table with probability proportional to alpha plus D times 4. Okay, so we subtract D from each of the existing tables, and we're going to add 4 times D to the probability of sitting at a new table. Okay. So with the Pitman-Yaw process, we expect that actually the number of tables is going to grow faster as compared to the Dirichlet process because the probability of sitting at a new table is growing. In fact, it's going to, as we have new and more tables, we're going to expect that the probability of sitting at yet another new table is also going to be growing as well. Okay, you can actually write down the ePPF, okay, under this two-parameter CRP, and you see that it looks functionally of this form, which basically means that it's a function only of the number of tables that's occupied in the Chinese restaurant and of the sizes of the tables that are occupied, okay, which means that it is exchangeable. Okay. And since it's exchangeable, then the same sort of story leads us to apply Definity's theorem and say that there's some underlying random probability measure that underlies this two-parameter CRP, and this thing is called the Pitman-Yaw process, which is a generalization of the Dirichlet process. Okay. So, as I said, one of the nice properties of the Pitman-Yaw process is that it has this power law properties. Okay? And you can see this from the generative process, right? Because firstly, with more tables, the chance of even more tables becomes higher. Okay, so we expect that there's going to be the increase in the number of tables is going to grow much faster. Okay, and secondly, because we are subtracting a constant d from each table, the tables with smaller number of customers are going to tend to be affected more by this discounts parameter, right? Because if we only have one customer sitting at that table and we're subtracting d, let's say d is 0.5, then we are removing half the probability for sitting at that table. Okay? But if the number of customers is 100, then subtracting a half doesn't really affect the probability of sitting at that table that much. Okay. So what this says is that tables with small number of customers tend to stay small, which means that if you couple those two together, what that says is that there's going to be a larger number of small tables, okay, which is kind of often what is observed in power law distributions. Okay. So here's just a few figures. So here we have a Dirichlet process, and again, customers are indexed on the x-axis, tables on the y-axis, and the boundary here, the front here is basically the growth of the number of tables as the number of customers grows, and that grows quite slowly compared to a Pitman-Yaw process that grows quite fast. So here it's kind of growing quite quick. Okay. You can see the slope is kind of increasing quite a bit. It's not increasing, it's not decreasing as quickly as in the Dirichlet process case. Okay. Of course, it's a generalization of the Dirichlet process because when d equals to 0, we just get back to the original one parameter case. Yep. So you can look at the number of tables, the growth of the number of tables as the number of customers grow on a log-log plot. And you can see that actually the Dirichlet process, this thing actually asymptotes to a kind of a line with a gradient of 0. But for the Pitman-Yaw process, it actually asymptotes to straight lines with positive gradients, okay, which kind of is one of the power laws that we see. Yep. So you can also look at the number of. So this is a plot, this is the usual zip flaw plot. Okay, so we are looking at the number of tables. This is the, wait, let me think. Yeah, okay. We take our tables and we say that, okay, there's one table of that size and maybe two tables of that size, three tables of that size, and maybe a certain number of tables of size 1. Size meaning the number of customers at that table. And we're plotting this on a log-log plot, okay, and you see that for the Pitman-Yaw process, this is basically a straight line, okay, which is basically Zipf's law. As I said, Zipf's law, I think, originally was used to model kind of the diversity of words in a language, and here we're comparing Dirichlet and the Pitman-Yaw process for modeling the growth of new words in the language as you see more and more documents in the English language. Okay, so in this case, what we're plotting is we're taking each word and we're plotting its frequency versus its rank according to frequency. And the black line is the empirical data, which is pretty much a straight line. The red line is the Pitman-Yaw process. That's the best fit. Okay, well, the best fit Dirichlet is not as good as the Pitman-Yaw. Okay. And you can also see power laws in other things. There's been some work looking at power laws in images as well. Okay. Yeah. So one of the applications that kind of combines the previous two. Yes. Okay. In this case, actually, we're doing simply maximum likelihood. So because we actually observe the types of the words in this case. So we can actually write down under the Pitman-Yaw process, the probability of our data is going to be given by this formula. Okay. And so we're simply going to be kind of maximizing the probability of the data with respect to alpha and d. And that's it. Okay. Yes? Okay. Because for the Dirichlet process, it's not able to model the fact that in the English language, most of the words that you see, at least on the web, you only most of the words that you see on the web you only see it once. Okay, so there's a huge number of words that you only see once and you never see again. Okay, and the Pitman-Yaw is very good at modeling that. It's very good at producing tables of size exactly 1, and it can produce a lot of those tables. With the Dirichlet process, it's not very good at producing those tables. So it's very difficult to force it to say that there's a large number of tables of size 1. That's why you get this curve that drops down like this. Okay. Yep. So there's a very nice application which kind of combines the two threads, the Pitman-Yaw process and the hierarchical Bayesian nonparametric model, where basically instead of a hierarchical Dirichlet process, you just put a hierarchical Pitman-Yaw process. Okay. And I'm going to skip through all this, but basically it works pretty well. Okay. In fact, I'm going to just give you the numbers. Okay. So here is a language modeling application where we're comparing a hierarchical Pitman-Yaw process against a hierarchical Dirichlet process for this language modeling application versus two of the state-of-the-art smoothing algorithms in language models called interpolated Nasonai and modified Nasonai. Okay? And again, those numbers are perplexities. So basically, how perplexed is your model? And the less perplexed it is, the better it is. And it works pretty well. It's pretty much less perplexed than the kind of the state-of-the-art methods. In fact, the fact that this number is actually pretty close to those numbers is actually kind of not a surprise. In fact, you can actually show that the Nasonai models can be derived as a particular approximate inference algorithm for the hierarchical Pitman-Yaw process. Okay. I'd like to also say a few words about this. So I think I mentioned this earlier. There's this in linguistics, but also in biology, people are interested in, if you see a sequence of things, what's the chance that you might see a thing that you haven't seen before? Okay, this is a problem of the discovery, estimating the discovery probability, the probability of discovering a new species or seeing a new word that you've not seen before. Okay, so one question what we would like to ask is, what's the probability of a new observation being of a new species? Okay. So there's a estimator called the good Turing estimator, which basically, interestingly, estimates the probability of seeing a new species using actually the following thing, n1 divided by n, where n1 is actually the number of species that are observed exactly once, okay, divided by the number of observations that you have so far, which is quite interesting because you're saying that the probability, you're estimating the probability of something that you've not seen that's occurred 0 times in your data using the number of things that you've observed exactly once. And you can generalize this to kind of higher numbers. So for example, the probability of seeing a word that has occurred exactly once, you can estimate it as basically the number of words that has occurred, using the number of words that has occurred twice. So you kind of shift this down a bit. Okay. Using Bayesian nonparametrics, you also basically can get this sort of estimates of new species, probabilities of new species. Basically, it's the probability of a new customer coming in and sitting at a new table. Okay. And there's been some studies which kind of tries to compare the two. It actually works pretty well. And a lot of this good Turing estimators, you can't generalize it to kind of more complex situations that people care about. So for example, you might say, if I go out into the environment and collect 1,000 new samples, how many species do I expect to see? Okay, there's no good Turing estimator for that problem. Okay, while there are estimators based on Bayesian nonparametric models. And you can show that the estimators that you get from Bayesian nonparametrics actually asymptotically will converge to the good Turing estimator in this simpler problem. Okay. I guess should I stop now or can I continue for another 5? Okay, cool. Yes. Are there any questions about this? Yes.
Can I ask a question about the language model?
Yes.
So, from the way that we last week actually, you mentioned Western verbs for using
Yes. Yes.
How would that be calculated here?
So, yeah, okay, I'll repeat the question. So last week, Leon Batu talked about methods for language modeling based on Western and Colbert. So those methods, you try to learn some sort of high-dimensional representation of each word and use that for modeling your language. So those things can work very well as well. In fact, I think I guess various people have shown that they can work better than these smoothing methods. But what is interesting is that they actually learn about different things, I think, because those methods, they try to learn representations of the words, but they don't try to model the power law behavior of your language. So I think one interesting direction of research which I've been thinking about a lot is, how do you combine the best of both worlds? How do you actually come up with a model that can model the power law behavior, but also learn representations of words? And I think that's kind of an interesting problem. Okay. Yeah. I should stop. Okay. Okay. I guess maybe I should just, maybe I should just stop now and take questions, and then I'll continue on this tomorrow.
Are there any questions? Maybe while you're still thinking about your questions, are there any questions in the observation lounge?
I think people want coffee.
No, we don't have any questions. Oh, there's one.
Okay, then let's first take your question from the lounge.
Okay.
So far, it's like everything is in like unsupervised manner. So can we use the same idea for supervised or semi-supervised scenarios? Thanks.
Yes. I guess a lot of these are, well, I don't know, unsupervised in the sense that there's no you're not really trying to model the distribution of labels given data. I guess there is a lot of supervised learning using a Bayesian Nonparametrics approach, and that's covered by all the Gaussian process work, I think. There's also been quite a lot of work in which people try to kind of combine Gaussian processes along with ideas based around Dirichlet processes, and those are what's called Bayesian nonparametric regression. So the idea there is that in regression, you might be interested in, given your input space, learning some sort of function which maps from inputs to outputs. Okay? But sometimes you actually don't really care about learning a function. What you care about is actually learning a conditional distribution, P of y given x, okay? Where x is now going to be your input and y is your output in a sense, but actually you don't want to learn the mean of this conditional distribution, which is what this function would be, but rather you like to learn about this whole conditional distribution itself in a non-parametric manner. And in certain applications, it's not the mean of this conditional distribution which is important, but the actual shape of it or the variance and so forth, I think. And those kind of like methods, many of them are based on this idea which I kind of skipped over, called dependent Dirichlet processes, I guess. Yeah. Yes.
So my question's from a while ago, and it had to do with the hierarchical Dirichlet process. And you made a statement that I didn't quite understand, which was you said because the smoothness of the H function, it meant that you had disjoint sets.
Yes.
And I didn't understand why that implied you had disjoint sets.
Okay. So if you go back to the HDP, wow, actually I'm going to go back really far. So if you look at the stick breaking construction, all the way back here, okay. So one way in which you could construct a Dirichlet process is the following. So we know that it is atomic, so it's going to be a collection of atoms with weights, with masses given by pi k, and the locations given by theta star k. And here, theta star k is drawn IID from the base distribution. Yeah?
Sorry,
the
the
mean?
base distribution was the Dirichlet process or the beta process, or what's
No,
the base distribution?
what's the mean of the Dirichlet? It's the, in the mixture model case, it is the prior over the parameters of the cluster.
Okay. Is that
Okay.
modeled by a distribution?
It is, so for example, in the mixture model case, if the parameters, if you are doing a mixture of Gaussians, then the Gaussian is parameterized by a mean and a variance, right? And H is the prior over the mean and the variance. Okay.
And because that's smooth, it causes...
So if H is smooth, if you use a smooth distribution over the mean and the variance, then every time you draw for each cluster a new mean and a new variance, it's going to be different from all the other clusters. Right? So if you think of a Gaussian, say, if you draw n samples from the Gaussian, all n samples are going to take on different values. Right? So here we have an infinite collection of samples drawn from your Gaussian. So all of them are going to take on different values too.
Okay, I can
Okay.
talk to you later.
Okay.
So this might also be I'll talk to you later question. Can you elaborate a bit on your thoughts on how to model how to represent words and combine it with power law behavior?
How do you model? Oh, like as in the Western and Colobert sort of thing. Well, we haven't been successful so far, so I guess maybe my thoughts are not very relevant. So what I guess we've been thinking along the lines of I guess Tom Griffiths and Sharon Goldwater. They had this very nice paper called Interpolating Between Types and Tokens. So there the idea is that you can, if you take any model, so for example, you could take Western and Colobert's model for words, and you could take that model and kind of add power law behavior into the model by adapting it using a Pitman-Yaw process. So the way you're going to adapt it is that, where's the, oh yeah, here. Is that, so typically if you have a model, you can think of it as it's a distribution over words. Okay, so the distribution could be, I don't know, what should I write down as the distribution? I'm going to write it as some distribution P. Okay, and you would model the words as, say, IID draws from this distribution, so XI. Okay, so, and if your model here doesn't have power law, then if your distribution doesn't have power law, then this is not going to have any power law behavior in your model. You could introduce power law by saying that I'm going to, instead of modeling it like this, I'm going to model it using G, okay, which is going to be a Pitman-Yaw, whose mean is P, and goes down like this. Okay, so that I'm kind of introducing an additional degree of variability here that kind of captures the power law. And the way it captures is that if you think about the generative process here, for the first word, for the first customer, it's going to sit at some table. So at the table, you're going to simply, the table is going to correspond to a draw from the base distribution, which is going to be P. Okay, so the first word is going to be drawn according to P. The second word that you observe could take on the same value as the previous word, or a new value drawn from P. And that's kind of described by the Chinese restaurant process. And because of the fact that the two-parameter CRP has this power law structure that actually induces power law in this overall model as a result. So we've been trying to play around with this, but I guess so far not successfully. Yes.
Sorry, when you say that that induces the power law, what exactly do you mean? Like the number of tables?
So
or something? Or?
what I'm saying is that is that if you look at the occurrence of words, if you look at the number of occurrences of different words, some words are going to occur a lot more frequently than other words. Okay? And there's going to be a very large number of words which occurs very rarely, which is kind of the Zipf's law plot that we saw, right? And we get the power law because in the Chinese restaurant process, right, we are creating these tables, which are a small number of tables which are very large with lots of customers, and those basically correspond to words which have much higher frequency than other words. Okay, and kind of that's how the power law kind of appears, I guess, in the model.
So some tables have lots of words, and some others have way less, or even one.
Yeah.
Cool. Thanks.
Maybe I can come back to the. Yep. So come back to here. Yeah. So. Yeah. So in this case, we have a small number of words up here whose frequency is very high. So we see those words a lot of times. So these are stop words like and the and him and she and so forth. Okay, so it's up here. And then over here, we have a very large number of words that occurs very small number of times. And basically, this corresponds to tables which have lots of customers up here, and a very large number of tables with a very small number of customers. Yeah. Yep.
So, as the other people can't hear you otherwise.
As I start using non-parametric priors, is there any diagnostic that I can use to figure out if my model is just misfitting to the data? I'm not using overfitting or underfitting, but can I detect misfitting, or is that essentially the same as MCMC convergence diagnostics?
I think there are probably different sort of diagnostics, because even if your MCMC is converging well, you could still end up with a model that is misfit because it's misspecified. Yeah, I'm not. I guess I haven't really kind of given this. I haven't been able to kind of say very clearly kind of how do you go about diagnosing misfitting. This is kind of in the Bayesian statistics literature is kind of an important thing that people think about, is like this idea of model checking, right? You have come up with your model, and you like to check whether the model fits the data or not. And if it doesn't fit the data, how is it not fitting the data, right? And I guess there are kind of some ideas for people kind of in terms of, so the idea is that you start off with a simple model and you look at how does it, whether it fits the data or not, and if it doesn't fit the data, how is it not fitting, and then you should expand the complexity of your model in a way that is kind of captures, kind of you try to move towards the data as much as possible, I guess. You're trying to improve the model where it is not doing well. Yeah, I guess there's those things, but I haven't really kind of been thinking that much about this sort of problems, I think, yeah. Yes?
Earlier you mentioned putting a prior on the concentration parameter, alpha. Is there any distribution for that in particular that's nice and tractable or anything, or is it?
I've just used like a gamma prior, and that works.
And then do you have to sample, or is there a?
I do sampling. I guess if you do variational based, there's also updates. I think there's a nice paper by Dave Bly and Mike Jordan, where they do variational Bayesian inference for DP mixtures, and they use a gamma prior, and they can kind of update the variational posterior over alpha in a closed form manner in that case. In their particular case, which kind of is very nice, I think. Yeah, I think it's just a one-dimensional problem, so you could specify whatever prior that you want that is sensible, and it works. Yeah. I tend to think of it as the way I specify the priors. I give a gamma prior over alpha, but given the two parameters of the gamma, that's basically an induced induced distribution over the mean and the variance of the number of clusters. And so the way I specify the priors, I think of what is the number of clusters that I expect to see in my data set, and how confident am I about that number. And I try to specify a prior on alpha that covers that range. So if I think that the number of clusters could be between 10 and 100, then I try to specify an alpha such that the induced distribution over the number of clusters is somewhere between 10 and 100. It has a support over that range. Yep.
Did you just say that I should use non-parametric priors when I believe the number of clusters is infinity?
Didn't I just say that I should be using non-parametric models when the number of clusters is infinite? So what I'm saying here is, I do believe that when I use the non-parametric approach, I do believe that if my data set is very large, then there could be there could be an unbounded number of clusters. Okay? But given a finite collection of data sets, there's still going to be a finite number of clusters. And the question is, given my data set of size 1,000, how many clusters do I expect to see, right, in that finite data set of 1,000?